Hello and welcome to our next lecture. Today we'll continue our discussion of the properties of the Fourier transform, of which there aren't many left. The next property is something that's reminiscent of the moments that we discussed for the Laplace transform. So the Fourier transform of a function that's multiplied by it to the power n f of t is minus 1 raised to the power n times the derivative with respect to omega n times of the Fourier transform of just a function. In doing so, we implicitly assume that the Fourier transform of f and the Fourier transform of the product exists. Just as in the case of the Laplace transform, the formula can be derived by starting on the right-hand side and differentiating the Fourier transform several times. The formula for the Fourier transform of the antiderivative is very similar to the formula we have for the Laplace transform. So if we try to find the Fourier transform of an antiderivative of f, this means that we're trying to integrate the integral multiplied by e to the minus I omega t dt, apply integration by parts, making u to be the integral and dv to be the e to the minus I omega t, which makes du to be just f of t dt, and v being minus 1 over I omega e to the minus I omega t. So this transforms into minus 1 over I omega integral from 0 to t of f of lambda d lambda times e to the minus I omega t evaluated from minus infinity to infinity. Minus minus makes it plus. The integral from minus infinity to infinity of 1 over I omega f of t e to the minus I omega t dt. And here's where things are getting very interesting. The antiderivative of f must exist, but it may not be the function from L2. And if we insist that the antiderivative is the function from L2, then this antiderivative as we vary t should converge to 0. We're asking a little bit more than all functions from L2 may provide, but it's a reasonable thing to ask. If we want the antiderivative to be the function from L2, then it should converge to 0 at both positive infinity and negative infinity. And since e to the minus I omega t always has absolute value 1, when antiderivative converges to 0, it converges to 0 at both ends. So assuming that the antiderivative converges to 0 at both ends, we'll have that this Fourier transform is 1 over I omega, the Fourier transform of just f. And this is the property that is exactly similar to the property we have for the Laplace transforms. A very similar property holds for the derivative of f. So if we take the Fourier transform of a derivative, and apply integration by parts by assuming that u is e to the minus I omega t and dv is f prime of t dt, meaning that du is now minus I omega e to the minus I omega t dt, and v is simply f of t. This changes this integral into f of t times e to the minus I omega t, evaluated from minus infinity to infinity. Minus minus makes it plus, the integral from minus infinity to positive infinity of I omega f of t times e to the I omega t dt. And just as in the previous discussion, we assume that f of t is a nice function from the space L2 that converges to 0 at both ends. Then the only thing that's left is the integral component, which is basically the Fourier transform of f. Here's an interesting twist. The Fourier transform is less applicable to solving of initial value problems because there is no place for the initial values. Hence, the Fourier transform is more often used in the analysis of the partial differential equations rather than in solutions. One last property that holds in exactly the same way as the Laplace transform property is the Fourier transform of the convolutions. The convolutions are defined differently this time. Since the functions are defined on the interval from minus infinity to infinity, the functions don't stop at 0, something that was happening with the functions that are in the Laplace transform. And because the functions were assumed to be 0 when you plug in negative values into them, the product f of t minus lambda times g of lambda was always 0 outside of the interval from 0 to t. This time this doesn't have to happen, so the convolution takes into account all of the values of f for all of the real values from minus infinity to infinity. So f star g of t is this time defined as an integral from minus infinity to positive infinity of f of t minus lambda times g of lambda d lambda. And this definition is not different than the definition from the Laplace transform. I repeat, we integrated for the Laplace transform from 0 to t only because that one of the functions, either f or g, will be exactly 0 outside the interval from 0 to t. And hence there was no reason to integrate outside of this interval. By applying the Fourier transform to the convolution, we get the integral from minus infinity to infinity of the integral from minus infinity to infinity of f of t minus lambda g of lambda d lambda multiplied by e to the minus I omega t dt. And I'm going to change the variable here. I'm going to say that a variable tau is t minus lambda, therefore t is tau plus lambda, and dt equals to d tau. Both of the variables go to infinity at the same time, so this becomes the integral from minus infinity to infinity of the integral from minus infinity to infinity f of tau g of lambda times e to the minus I omega multiplied by tau plus lambda d lambda d tau. So this can be written as a product of two integrals. Since now the integrals are completely decoupled, f of tau times e to the minus I omega tau d tau times the integral from minus infinity to infinity of g of lambda times e to the minus I omega lambda d lambda, which is just the product of the Fourier transform of f with the Fourier transform of g. Let's consider a short example. I know that the convolution of this is going to be the tent-like function that we considered in the previous lecture. But today I want to find this convolution with the help of the Fourier transform. So the Fourier transform of this function in convolution with itself is going to be the Fourier transform of the function chi squared, because that's going to be the product of the Fourier transforms of the same function. And from the previous examples, I know that the Fourier transform of this function is sine of omega over 2 divided by omega over 2 squared. Sine squared can be converted in accordance to the double angle formulas into 1 minus cosine of omega over 2, and the bottom stays omega squared over 4. So this can be written as 2 over omega squared multiplied by 1 minus cosine of omega. And according to the previous examples, this was the Fourier transform of the tent-like function, the 1 plus t, on the interval from -1 to 0, and the function 1 minus t on the interval from 0 to 1. Therefore, the convolution of the function chi with itself is just this function. This function was called f of t, and that's what it is. The last example for today is just an interesting fact. So I want to consider the Laplace transform of so-called Gaussian function. So when a is greater than 0, this function has this profile. This function doesn't have any oscillations at all, yet its spectrum is quite surprising. So what would be the f hat of omega, which is the Fourier transform of this function, which is the integral from -infinity to infinity of e to the minus at squared times e to the minus I omega t dt. Well, one thing I want to do is I want to join the exponential terms. So this is just going to be the integral of minus, and then inside the parentheses I have at squared plus I omega t. I want to simplify the expression by using completion of square. I'm going to move minus a outside, and what's inside is simply t squared plus I omega over a t, plus I have to include I omega over 2a squared and subtract I omega over 2a squared to balance out the equation. The last term I'm going to factor out outside of the integral. So before I do that, let me count the minus signs. I have a minus sign here, I have a minus sign here, and I have a minus sign that comes from the I omega squared. So this becomes e to the minus a times omega over 2a squared times the integral from -infinity to infinity e to the minus a, and then inside I have simply t plus I omega over 2a squared dt. So it seems like I'm integrating the same Gaussian, except that now this Gaussian is being shifted up in the complex plane in the imaginary direction. Had the shift happened in the real direction, had I not had the I in this term, then we would have seen that shifting the Gaussian to the left or to the right makes no difference to the integration of the entire real line. However, when they shift up, it's not so obvious. The theory of integration of functions of complex variables says that this integral is still the same as the integral of a single Gaussian. So this is going to be e to the minus a times omega squared over 4a squared times the integral from minus infinity to infinity e to the minus a t squared dt. Again, it's not obvious why this is true, but I hope you have enough trust in me and you can just believe me when I say that it is. If you don't have any trust in me, you can trust the mathematicians who derived this result before me. I'm not going to derive the computation of this integral since it should have been done in your multivariable class or any class on the probability theory that you may have taken, and I know this integral is just square root of pi over a. So we end up with e to the minus, a and a cancels out, so I get omega squared over 4a multiplied by square root of pi over a. So you can see if a is equal to 1/2, then the Fourier transform of this function is exactly the same as the function itself. F of t equals e to the minus t squared over 2, and f hat of omega equals square root of 2 pi multiplied by e to the minus omega squared over 2. So we can see that the Fourier transform of this function resulted in just multiplication of a square root of 2 pi. So we can say that this is an eigenfunction for the Fourier transform. And if you're curious, the Gaussian function is the only function that has this property, that the Fourier transform of it is exactly the same type of function as the function you started with. Well, this is it for today. I hope you enjoyed today's discussion, and I'll see you in our next video.